Okay, in lab, we observed a LR circuit. L is about 1/3 of a millihenry, and R is about 10 ohms. Well, let's keep that. Okay. Now, when we observed it, we had a graph that looks something like this. Actually, it was a square wave, but it doesn't really matter for what I'm saying. Okay. And we changed from like 0.2 of a hertz to 2 hertz driving voltage. And when we did, it appears that the amplitude got a whole lot less. Now the frequency stayed the same, so I shouldn't be. Actually, frequency did increase. So we increased the frequency, and that decreased the amplitude of the circuit, of the current, okay? For these values of L and R, that should not have happened. So, two things. We were not measuring the voltage across the circuit. And it could well be that the instrument, the function generator, changed its output voltage when we changed the frequency, okay? And again, we did not check that. We're just looking at the current. I guess we're looking at the voltages in the two components. We had 2 voltmeters hooked up. Okay, so we had a voltmeter across the inductor, a voltmeter across the resistor. But they both did this sort of thing, I think. Okay. Now I was expecting a change when we got near the time constant for this circuit. Well, let's see what the time constant is. Let's see what the equation tells us. First of all, we've seen this a number of times. L di dt plus R times I is voltage of the source. R times I, of course, is the voltage drop across the resistor. And L di dt is voltage drop across the inductor. You know that when you change the current through a coil, it produces a back EMF. It slows everything down. Okay? That doesn't slow everything down, but it puts a lid on things. It's like a resistance. It's a capacitive reactance. We'll see what that is in a minute. Okay? So when we solve this equation, well, we could start out with the voltage of the source and see what the currents ought to be. But what we're going to say is assume usually I is expressed as a sine. It could be expressed as a cosine. It doesn't matter. But I'll go with convention and express it as a sine of omega t, where omega is the frequency of the source, and that's determined just by how you have, by what you do with the function generator. You turn the dial, you press another button, just what we did in lab, okay? So we changed omega, and it caused this, just by changing omega from 0.2 of a hertz to 2 hertz or something like that, okay? Shouldn't have happened. You're going to see why. If you assume that I equals this, and L di dt plus Ri equals omega A L cosine of omega t, because of course, if I equals sine of omega t, di dt is omega times the cosine of omega t. So I'm going to get the A out of there, omega L cosine of omega t plus R sine of omega t equals voltage to the source over A. A is just a constant we throw in there, and we can adjust that constant just by turning the output up or down. We get more or less current. The solution of the equation, though, the essence of the solution doesn't depend on A, just the amplitude of what we get. And I guess I'm not going to go there. Okay. The voltage of the source over A, we can write V naught over A I just wrote cosine of omega t plus phi because that's what I'm used to thinking in terms of, but it's a sine of omega t plus phi, where phi is the phase angle between the actual voltage that's being supplied by the function generator and the current, okay, which is a sine of omega t. I could call it I naught sine of omega t, probably should have. Now, a couple things. Cosine omega t and sine omega t are just numbers. Their numbers have changed with angular frequency omega and so forth as time changes. Omega L and R have to have the same units. Okay, I'm not going to get into detail on the units. You can work that out. It's easy. But that means omega L is like a resistance. Okay, so this is a resistance. And omega L is a number with units of resistance. We call it X sub L. It's a reactance. It acts like a resistance, and it results again from the back EMF you get from the changing magnetic field when you change I. Okay. And that opposes a change in current. Okay. So it's like you have this and this. Okay, well, I want to draw a picture now. T equals 0. I'm going to represent I'm going to label this R for the time being. And I'm going to label this L. And I'm going to say that this picture is rotating let's say counterclockwise at angular frequency omega. I'm going to impose a y-axis up here. Taking liberties, it's not really our sine of omega times 0, but r would equal 0 here. That makes sense? Just think the unit circle picture. The sine is the y-coordinate. That's your basic definition of sine and cosine for analytic trigonometry, which I hope you know at least fairly well. Okay, hopefully very well. Up here, L sine omega t would equal L. Actually, let's say, keep the units consistent. Let's call this L omega. And to try and invoke L here. Okay. Now, when the vector's in this position, its y-coordinate is just whatever the magnitude of the vector is, right? Okay. And you have a result. You have a resultant vector. Which in general is r sine of omega t plus L omega cosine of omega t. But when t equals 0, we'll just put in 0 for t, and that matches this picture. This is going to be your net current. I'll call that I of 0 equals this. Magnitude of this I of t vector. Oh, wait a minute. It's not what I want to call this. It is not your current. Um, not having the greatest day today. Just bit of sleep deprivation over the weekend. Not too bad, but not totally with it. It's no excuse. We'll just call it Q for right now. Q of t has a magnitude. This is just the hypotenuse of this triangle. L omega quantity squared plus r squared. And I of t, well, there's another angle here. Angle phi is the inverse tangent of L omega over R. It should be obvious. Phi is this angle, the tangent is the opposite side over the adjacent, or it's y over x. Okay? And hopefully that's totally ingrained, because you run across it a lot in most fields. Okay. As if I knew most fields. I think you run across it a lot in what I know of most fields, and some fields I know more about than others. Okay? So I'm not talking about your specific field, unless it's one that I know a little bit about. Okay, well, anyhow, phi is the inverse tangent of L omega over R. Okay? And your current is a function of T. This current in time T, this vector is at angle phi with the R vector. And the R vector really represents the current. So I'm going to relabel. Might have confused things by doing this, but I don't like that. What this really is a voltage across the resistor. Okay. And what you really have here is the voltage across the inductor. You can read all the details, and there's a standard letter that's used for this, but I haven't looked at it in a while. So it just isn't there for me today. I'll call it Q of T. The actual current okay, I'm saying wrong things here. Let me stop for a minute. If I could get back to Zoom, I could pause this thing. Okay, I was trying to shortcut a few things and then I confused myself. So I'm not quite all here. Okay. So now, same picture, same hypotenuse. It's just what do we call this thing? And I'm using Q when I'm really wanting to use reactance. I mean, I used it here, I used X, right? I couldn't think of what letter to do here. That's where I am today. I'm sorry. This is reactance, and this is reactance at time zero. Okay. If I multiply the current times the resistance, I get the voltage across the resistor at that instant. Remember that the current is a sine of omega t, whatever A happens, some constant times the sine of omega t. So that the voltage across the resistor is changing in time. This is just a picture of what it looks like at t equals 0. Okay. could have just drawn the whole picture, but I didn't want to do that. Okay, well, here's the bigger picture. Now you have VR and VL and the resultant. And I guess to be consistent, I'd multiply all this by the current. I'm going to leave it the way it is. Okay. Now here's a picture. At time omega t. Now you're familiar with the circular picture of simple harmonic motion, right? Okay, so we have at some time, let's say a different omega t, but here's an omega t. The y coordinate here is a sine of omega t. And this is the unit circle picture. Just sines and cosines of it changing. And, okay, the angular frequency is omega, that's like in radians per second, times like in seconds, you get angle in radians, and that whole picture. So I'm trying to invoke that whole picture. I'm going to go back here and change one thing I wanted to change. Okay, this would be source voltage at time zero. We just multiply this reactance, or yeah, we just evaluate this multiplied by I max. Right here's your phase angle phi, which is still the inverse tangent of L omega over R. That doesn't change. So what we've done is we've just taken this picture and we've rotated it through an angle omega t. And I don't have room to label it. I'll just say it's I max times your reactance. It's kind of like an effective voltage reactance. Here, is your Vs of t. So this whole picture here remains congruent to the one I had here. It doesn't look congruent, but it is. And you keep rotating around, what happens to voltage of the source? Well, it keeps going around here in phase space, but the actual voltage is the y coordinate because we're doing a sine. And the actual voltage is going up and down here. Okay, that's the phasor picture. For RL. Now, what I want to do, if VL is very small compared to VR, then this vector is practically the same as just VR, right? It's not out of phase, has whatever magnitude you get, okay? Phase angle is the arctangent of L omega over R. I'll just leave it like it is. What's L over omega? Did I say L omega over? Yeah, I did. But what's L over R for this circuit? Just give me a number. What do you get if you divide this by this? Don't even worry about the units. They come out in seconds. I do want you to worry about them. But right now, just take my word for it. They come out in seconds. I saw reciprocal seconds. What do you get if you divide 1/3 of a millisomething by 10? You get 1/3 of 10 to the negative third, 10 to the negative second, 10 to the negative fourth, okay? Which is like 3 times 10 to the negative fifth, okay? So what I'm going to say here is, okay, now 3 times 10 to the negative fifth reciprocal seconds. Now compare that. And that's like 3 times 10 to the fifth. And to the negative fifth. Think of it as 3 times 10 to the fifth radians per second because that's the way it works out. Make sure we can see that, yeah. Okay. So on our picture here, we have our resistance, 10 ohms. Okay. We have our L omega. I'm looking for board space. L equals 1/3 of a megahenry and R equals 10 ohms. This is 3 times 10 to the negative fifth radians per second. Okay. So your phase angle I'm about to write is kind of almost correct, but not really. Small angle approximation, it would have been correct. I'm gonna. Do the intermediate step. Finds the inverse tangent of L over R times omega. Okay. Omega corresponding to, let's say, 20 cycles per second is 60 pi radians per second, right? Well, you take 60 pi, which is about 200, and multiply by 3 times 10 to the negative fifth. You can do the calculations. Pi is going to be the inverse tangent of like 6 times 10 to the negative third. Okay. Small angle approximation, that's about 6 times 10 to the negative third radians. About 6 milliradians. How big's a milliradian? Yeah, well, a radian's like from here to here, maybe. A thousandth of that, you couldn't even draw it on the picture. You'd have to have very fine lines in a magnifying glass. Okay? So you should have essentially no change in the circuit at 20 hertz. Okay? Now figure out what you get at 10,000 hertz. In other words, your picture. Again, phi would be practically zero. VL would be so tiny you couldn't draw it. Your voltage is just the voltage across the resistor. It's as if the inductor wasn't there. As if there's no inductor. If omega is 10 kilohertz, then what do you get for L over R times omega? Just figure it out, ballpark it. 10. That's just 10 to the fourth cycles per second, right? So what's omega? Be 2 pi times that, right? Because that's in radians per second. Cycle is 2 pi radians. Okay. Okay, well, I'll help you out with that. I'm sorry. If the frequency is 10 kilohertz, then omega is about 60,000 radians per second. What do you get if you multiply 60,000 by 3 times 10 to the negative fifth? And L over R is not in radians per second. L over R times omega would be in radians. It should be 3 times 10 to the negative fifth seconds. And I did something wrong over there too. I'll correct it. You still get the idea. Got a number? Number I get 6 times 10 to the fourth multiplied by 3 times 10 to the negative fifth is 1.8. Okay. It's actually 18 times 10 to the negative 1 because you get 10 to the negative fourth, 10 to the fourth and 10 to the negative fifth. It's an inverse tangent of 1.8. Okay. Now, what's the inverse tangent of 1.8? That means like you've got an angle here where the y coordinate is 1.8 times the x coordinate. Okay. That isn't quite drawn right. I'm going to say, though, that that's approximately maybe 67 degrees. Now, anybody do that? Okay, what'd you get? First digit. Hold up fingers. First digit. 6. Second digit. Don't talk. 1. Okay. That's a better finger. Okay. 1 what? 1 6. Second digit. 1 1. Are you in degree mode or radian mode? You're in degree mode. You're getting the arctangent of 1.8 is the number whose tangent is 1.8 looks a lot like that. So I'm not sure I believe it. Let me just double check. Okay, I'm not sure about somebody got 0.1 something or 1 something, but 67 degrees isn't that close. It's more like 61 degrees. It wasn't that far. Okay. That means that your inductor is going to be 61 degrees out of phase with your resistor. Okay. As this thing goes around the circle this way, your inductor leads your resistor, right? In other words, the phase of your resistor will be 61 degrees later than the phase of your inductor. Now, the purpose of all this is not so much, I want you to have this picture. I'm probably not going to test the over phasers just because we're close to the end of the semester and there are other things we've got to talk about. And I should have developed this a lot quicker, but I did it off the top of my head. And I do apologize. I'm not thinking well today. Even with a 61 degree angle and the magnitude of your L omega, I could put that down, L omega is approximately 60,000 times a third of a milli. A milli would give you 60/3 of that. Omega is about 20 ohms. So this VL, remember your VR is voltage cross resistor. Well, it's 10 ohms times whatever your maximum current is. It's the length of this one. And this one is 20 ohms. So what that tells you is there's VR, there's VL. You do the hypotenuse and you get 61-degree phase angle. It's hard to read that. Do it yourself. And you have your total reactance. You've got like 10 ohms this way, 20 ohms this way. You have the squares, you get 500 ohms, and that's about 22.3 ohms. What that tells us is that your reactance is about twice as great as it is if your frequency is 20 hertz. Okay. So if you go from 20 hertz up to 10,000 hertz, you come down to a little less than half of your voltage. The amplitude of your voltage is going to be about half. Okay. That's totally inconsistent with what we saw using the circuit board. Okay. So the assumption that the voltage output of the function generator was constant is a faulty assumption, I think. I haven't looked it up. I'm going to check it out. Okay. Now, what I do want you to understand is a solution to this equation, and also the RC and the LC circuit. Okay. As it turns out, I'm just going to give it to you in a nutshell. This is like the resistance that's created by the inductor. X sub C is like the resistance that's created by the capacitor in conjunction with the resistor. If you change the resistor, you change this. Your total, well, I guess I better do a picture. If this is voltage across the resistor, and this is voltage across the inductor, the voltage across the capacitor is down here. Now, why is that? It's because if you have R sine of omega t, minus 1 over omega times I guess I better write it all out. Let's see where the C comes in. Okay, you have Ri plus Q over C equals total voltage. If I equals I max times the sine of omega t, then Q equals negative 1 over omega times cosine omega t times I. You can just check that out. There's a sense I equals dq dt. So you can check out that the derivative of this equals I, dq dt equals I. Just take the t derivative, you're going to get negative omega sine omega t here. Multiply that by a negative 1 over omega, you just get sine omega t. You just come out with the current, okay? I'm not going to draw the whole picture and all the projections and everything, but this follows immediately, okay? Voltage across the capacitor, legs the voltage across the resistor because negative cosine legs the sine by 90 degrees. It's always 90 degrees. These are always right angles. So here's VR, and here's the total reactance. Now, if you complete the solution of this equation, the R is going to divide both sides. You get an RC in the denominator there, and it falls right out. It falls right out. It's very, very straightforward. So your reactance is your net reactance. It's L omega minus 1 over RC. That means that the magnitude of your maximum voltage is going to be magnitude of this vector going to be your maximum current multiplied by not organizing this well at all. And I shouldn't use X for this. My notation's all messed up. I don't have a good notation for what this is. I'm just going to say you've got L omega minus 1 over omega C. I'm going to revote this. At I max R here, you've got XL minus XC here, just the resultant of these two vectors. Okay, XC might be bigger, might be smaller than L omega. So this vector could be this way or this way. Or it could be zero, in which case you've got resonance. Which I'm not going to have time to talk about. But the only difference between what I'm going to write here and what I wrote before is I don't have a symbol for XL minus XC. But I've got a right triangle with legs, I max times R, and I max times XL minus XC, which means the hypotenuse is this. And the phase angle is this. Just opposite side, which is this, over hypotenuse, over adjacent side, arctangent. It's more than I intended to say, but I kind of got off on it. Off in many ways. I kept pursuing it and I made a lot of mistakes in my notation and in some of what I said, and I apologize for that. If you're going into anything related to electrical engineering, you're going to want to follow up and make sure you understand this. It's going to be helpful too when you get into analyzing circuits. Or if you have a circuits course in your future, you have a really good start if you understand this phasor picture. Okay? Okay, now we'll talk about the exam. The assignment for Thursday is kind of the same as the assignment was going to be for today if I'm not here. Okay? So it's questionable whether I'll be here or not. Right now I'm planning to be here, but there are things that might pull me away. They're big things, so I don't abandon you for small things, unless I'm in the mood. Okay. My basic philosophy on the exam is going to be largely based on the introductory problem sets, which you want to really understand thoroughly, symbolically, intuitively, etc. Okay? And we've gone beyond the introductory problem sets. Like this is way beyond the introductory problem sets. But a lot of stuff like rate of change of magnetic flux, you got several problems on that. And I don't say that that's a derivative, but the instantaneous rate of change is a derivative. And if you understand calculus, you understand why. If you don't understand why, you need to understand calculus a little better. Okay? I mean, just in general, in the future. Okay? But you know, what's a derivative? It's a limiting value of the rate of change. So, if that isn't, keep thinking about it. Go back and look at your first year calculus. Look at how derivatives is defined. Limit as delta x goes to 0 of f of x plus delta x minus f of x. That's a change in the value. It's a change in y. Divided by delta x, it's change in y over change in x. It's a rate of change. So whatever your functions are, that definition tells you what the derivative means. In the case of flux, the derivative is phi of t plus delta t minus phi of t over delta t. Limit as delta t goes to 0 to give you the instantaneous rate. That limiting process, you really need to be sure you understand that, just because otherwise there are things in engineering and other fields that you're just not going to be able to conceptualize well. Just stay in the dark if you are in the dark. And I don't think everybody here is in the dark. Sometimes I'm surprised. Okay. Surprised at things that people don't retain from their first year calculus course, much less second year courses. That's a little tougher. I mean, we're doing multivariable calculus, some of you. It's a language of a lot of engineering, but you don't really understand the language until you start using it. So you develop the basic ideas, basic techniques, so you can read the stuff and ponder what they mean. Well, that's kind of a sermon, so let me forget that for now. But where we've gone beyond the introductory problem sets, I expect you to be able to go beyond the introductory problem sets. If you understand the introductory problem sets, there's very little in this course that you won't understand. Now, to understand what we just did here, you have to understand vectors pretty well, and you have to be able to solve those first year calculus level equations. Okay. Your assumption is in either of the equations, standard assumption is that R is that I is some multiple of a sine of omega t. Everything falls in your lap. It's really very simple. Translating that into the picture, well, that's a little bit of a challenge. Then understanding what happens as this thing rotates at angular frequency omega. That's based on an understanding of the unit circle picture, the parameterization of a unit circle, which is important for multivariable calculus, okay, as well as for physics, and for understanding waves. So I'm hoping they'll be here Thursday so we can talk to everybody about relativity a little bit, so you understand a little bit more about set 7, although it's all there. And if I don't talk about it, it's less likely to appear in any challenging form on the exam. Okay. But basically everything in the other 6 sets. Make sure you understand them all. Got one other comment. if you have a mechanical oscillator that does this, okay, you could have a decrease in amplitude for given energy, given rate of energy input, okay? Because you have something mechanical that doesn't want to change direction very fast, okay? Now, if you get a high inductance, it doesn't want to change direction very fast. That takes some energy, okay? But with low inductance, I don't have an explanation for that. As a mechanical system, I have one pretty quickly. Oscillating a lot faster, takes more force. Achieve a quick turnaround. And it kind of follows. So here's an analogy between electrical and mechanical stuff. Like the differential equations are practically identical. You know, the L di dt plus Qi plus Ri plus Q over C thing equals whatever. It's just like a mechanical resistance, okay? Which is restoring force times your second derivative of position, okay? Plus drag force times the first, drag coefficient times the first derivative, okay? And so you have total analogy in the equations. The thing that comes out of electrical systems is that phasor diagram and the relationship between omega and the IDT and energy you got to supply to power the coils, the inductor. Okay. Any questions? I don't have the exam made out. Might be several days before I do. I'll try to keep you posted. There's a document that I started last night that kind of surveys the introductory problem sets. I can't guarantee I'll be able to finish that, but I think it will. Okay. And questions and statements and stuff that you should try to understand. Okay. Well, hopefully I'll be here Thursday. And if not, I'll communicate. And the exam will be in the testing center next week. Mostly, again, over introductory problem sets and lab situations. I didn't mention lab situations. So I'm going to review your lab activities and can answer questions related to the labs. I'll try to get you some sample questions on the labs too. And I've been a little slow on that. Simply because I think you guys are, I don't want to overwhelm you until the very end. Don't overwhelm you now. Y'all have been good. Okay. So hopefully see you Thursday.